what I'm trying to give you here is kind of a break them down into 7 different classes. I mean, this is just a blanket statement. That's why there's no such a way that I can just do one sentence to describe everything. I think there's no such thing as this. I can probably give you too much good idea what's going to happen, but there's always something can fall in between, so you guys have to always be careful with that. But the point is it's always alkyl halide. That's the base, the substrate, right? We are reacting with the alkyl halide. And some reagent, that reagent could be seen as a base, that reagent could be seen as a nucleophile, right? Depending on what label we put on it, it could be different reaction. If it's a nucleophile, then we're going to get the substitution reactions. If it's a base, then we're going to get the elimination reactions. The question is, how are we going to figure out the reagent is provided it? It's going to be act as a nucleophile, it's going to be act as a base. That is something that you have to figure out. So that's something that I'm looking over how we're going to sort it out. Anyway, we make those two meet, and then that's going to become a product. First thing I want to say that is a strong reagent will get the job done first. Strong base or strong nucleophile in the presence with a weak nucleophile, weak base, these things has to be the strong one, because the later one get the reaction done first. So if somehow you got more than one reagents in the equations or reactions, then what you need to pay attention more is a strong one, right? The weak one's not going to make things go faster. It's a strong one, it's the one that's going to make the reaction go faster. And they're the one who's going to go to the finish line first before these guys try to do anything, right? So don't get confused by the several things in the same reaction, then, which one do I need to use to finish the product? Strong one, you see it, that's the one that goes first. Strong reagents, like a strong nucleophile, weak nucleophile. If you're not quite sure what's a strong, what is weak, I want you to pay attention to the table we talked about, kind of examples of the strong nucleophile, moderate nucleophile, weak nucleophile. Those will give you pretty much good idea what those things are. Most of the strong nucleophile or strong base, they are charged electron-rich species, right? Sometimes they're neutral ones too, but mostly charged. And the weak nucleophiles are something like alcohol, water, those type of neutral oxygen-based molecules. Those are something we consider weak nucleophile with base. But strong nucleophile, strong nuke base, they will promote SM2 into elimination reaction. And then if they don't have this strong one, then it's going to be SM1E1. When you mix strong one, weak one together, they don't go for the E1 SM1 because it prefers it. No, it's because there's nothing else can happen, right? So if there's something else can happen, that will happen first, and then at last resort, SM1E1 should happen. So those are something that you should consider. A strong one will get the job done first. The question goes, but it's not only the strength of the reagents is the only factors. Alkyl halide also matter. If you remember that SM2 reactions, the least substituted alkyl halide is the better. So you got strong nucleophile, before we get there, strong nucleophile, strong base. That reagent, if they have a both possibility that they will make an E2 go, they will make an SM2 go. Then how are we going to figure out is the E2 going to be predominant pathway or the SM2 is going to be predominant pathways? How are we going to figure out? That is something that you also need to pay attention to the other side, which is alkyl halide. If you see the strong base and nucleophile reacting with the primary alkyl halide, then I would say probably SM2 will happen first, right? Because SM2 reactions are very sensitive to the substitutions. And if you remember the E2 elimination reactions, they prefer tertiary alkyl halide because they can make a more substituted double bond. If they react with the primary alkyl halide, they're going to make the least substituted double bond, so they're not to be happy about it. So if you see the primary alkyl halide and then possibility of the strong nucleophile as a base, then E2s are probably not going to happen, most likely SN2. Then this can also play the other way. You got strong base and strong nucleophile, and then you are reacting with the tertiary alkyl. Remember the tertiary alkyl has two hindered, so SN2 reactions doesn't happen to it. So even though you got strong nucleophiles with a tertiary alkyl halide, then no SN2, only thing possible is an E2 elimination reaction. So things can be narrowed down further this particular way. If the reagents could be ambiguous, you may have a certain reagent really prefer to be strong nucleophile, not a strong base. There's something like that there, maybe we're going to talk about it later. There's a strong base, not a good nucleophile, also exists. If you have that, then that's the one that narrows the passage. But if you have a reagent that can act as a both, then the alkyl line could narrow it down where it's going to go, just like with this. And tertiary alkyl line and strong base nucleophile, then I would say that maybe you need to elimination will happen predominantly, not an SN2. And obviously, then the question is a secondary. Secondary is a very gray area because the secondary alkyl lines, remember that they're in the middle. So they can go to an SN2, they can go to an A2 at the same time. So you got just normal secondary alkyl line, reasonable strong nucleophile, strong base. My expectation is both will happen. So that would be a little bit difficult. And then if it's a truly difficult one, we wouldn't be able to ask the question, right? Or expecting just the one answer. If we're expecting more than one answer, two answers, maybe E2 and SN2 both product at the same time, then yes, we would ask it. But if you want you to just pick one product, then there's no way I can answer this question because it's valid. But there are certain situations that even though the secondary alkyl line can go both ways, reagents can narrow down. You could have a potentially strong nucleophile, but that turns out to be not a strong base. Then only SN2 can happen. It's limited down by the reagents. At the same time, there's such a reagent that can be called as a strong base, but not a nucleophile. Then you can only make an E2 elimination acid. So things can be narrowed down either way by the alkyl side or by the reagents. And you have to look for those things, calculate, and figure out what you actually have in the question. SN1E1, you know that those things happens together at the same time. It's really difficult to separate them. There are situations I could think of, maybe maybe SN1 happened, not the E1 happened. It's probably not having an adjacent hydrogen. If there's no adjacent hydrogen, there's no way you could have an E1 elimination happen because double bonds in the two carbons there, right? So that might be one of the ways that E1 can be shut down. But is there any way you can shut down SN1? You don't know. I mean, maybe there's some way. I haven't thought of that easy. So if you ever find out, let me know. But anyway, these are just a little bit of flow chart to give you an idea that you have to put in the right groups so you can figure out what can happen. Easy to say this way, but the real thing is you've got to use that to the actual example to figure out what's going to happen. So I will give you certain ideas on those examples. I mean, here I talked about, these things are pretty obvious, but those things, what are the strong nucleophile but not a good basic one, right? What are the strong base but not a good nucleophile? What are those things, right? So that's what I'd like to show you that idea that is a kind of example. This is a secondary of the health, right? As I talked about, secondary of the health, like if you have a strong reagent, that sodium methoxide, that is a strong nucleophile, right? But sodium methoxide is also a strong base. So that thing can go either way. It can make an SN2 happen, it can make an E2 happen. If you ask me between SN2 and E2, which one is going to be major between these reactions, I don't know, because I cannot figure it out. So if there's equal chances, then there's no way you can pick out one over the other. If you're using a weak reagent, like a methanol here, that makes it an E1 SN1 reactions. We already talked about SN1E1 both happening together. Yes, and both happen together. And you know, when it's kind of silly to find out SN1 is going to be major or E1 is going to be major. We're not going to talk about that because both will happen at the same time. But similar things can happen even SN2 and E2 because of secondary, very simple secondary line, then both will be possible. SN2 is possible, E2 is possible. I don't know which way it's going to go. And I'm truly expecting I'm going to get both. But what if you are using not this reagent, something else? Then can those things narrow down? So that's what I'm getting into. We learned at the time of the strength of the nucleophile, we talked about it. There are certain things that can be called as a strong base, but not a nucleophile. That's a bulky base, right? If you remember that, these are p-butoxide, p-butyl groups are huge. So even though you got oxyanion, that could be strong nucleophilic center, but p-butyl groups it needs to carry together makes it very difficult to approach the target. So that's why it becomes a non-nucleophile. P-butoxide, bad nucleophile, still very, very good base. And then isopropylamine, that is also considered as a very bulky base, not a good nucleophile. And the conjugate base forms of that, there's lithium diazopolyamide, there's classic examples of the strong base, not a good nucleophile. And then triethylamine, 3 ethyl groups on nitrogens, it also makes it bulky, and then basically dimethylpyridine turns out to be very bulky, but not a strong nucleophile. So whenever you're using that, these things doesn't make an SN2 drug. Even though this is a good substrate for the SN2, but this, because of that, doesn't act as a nucleophile, what we're going to only see is an elimination rate. Right? So that's an example of the reagent can narrow down. But can we expect something opposite? Do we see certain reagents can be called as a strong nucleophile, but not a good base, right? Then only SN2 can happen, not the elimination reaction. There are certain things exist. So that's what I'd like to give you. These things is called the azide. These are resonance stabilized anion there, nitrogen anion. The sodium azide, this azide is a very, very good nucleophile, but not a good base because they're kind of salt. You don't consider table salt is a base, right? They maybe consider a very, 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 very weak base, depending on the Dresser-Lowry theories. But in practical sense, they are a good base. And just like that, these are salt. So that's why they don't typically pick up the hydrogen from the molecule, but they are really good nucleophile. There's something like that also exists, sodium cyanide, right? With cyanide also resonance stabilized anion that can be considered a very, very good nucleophile, really good nucleophile, but not basic at all. This is also salt. The other things are not a salt, but they have a very weak base system. I'm not saying that these things are not basic. These things are more basic compared to the other two, but compared to whatever we talked about with the methoxide, these are strong base. I would consider those things weaker than milder base. So, like the thiolate with the sulfur get negatively charged because the size gets bigger and becomes stabilized. That's the reason the sulfur anion doesn't become a strong base. They rather because they get stabilized by the size. And then can be a very good nucleophile because if you remember that when the size gets bigger, basicity goes down, but the nucleophilicity goes up because it becomes a more soft, polarized molecule. So that's why sulfur anion, really good nucleophile, very weak mild base. I'm not saying they're not basic, but they're kind of basic, but not as good as this. Just give you how much weaker, about 1 million times weaker base than this one. That's about pKa of 16. This is a pKa of like a 10. So about 1 million times weaker base. And then this is a carboxylate. If you know that the carboxylic acid is an acid by the conjugate base form, that anions are going to be an oxygen, but remember that these are resonance stabilized. The negativity charges, that's solely sitting on the one oxygen. They're spread by 2 oxygen pairs. Each one carries a half the density. So that's the reason the basicity goes up, because they're stabilized anion. But because of that, they can act as a somewhat good nucleophile. I wouldn't say that these are good nucleophile. These are good. These are superb nucleophile. These are good enough, still good enough, but the resistance also goes down. So that's why I'll say if you have something like this, then most likely you're going to get the SN2 reaction. You don't have to worry about E2 elimination reaction. Because these things doesn't have a basis to make an integral. Any question? There are probably other situations that you may need to concern, which is difficult to say if it's an intramolecular reaction. These I kind of touch bases very briefly. When most of the time you see there's an alkyl halide and there's a base or nucleophile there in different molecules. So you can recognize this is A, this is B. When they come together, you're looking for C. But sometimes you only see one molecule in the reactions, and then yet we are expecting you to figure out what's going to happen. So most of the time, those in that situation, that one molecule may have a alkyl halide and a nucleophile together, right? And when you see that, the intramolecular reaction happens. The alkyl halides make this carbon electrodeficient, and that's the one this nucleophile gonna attack. It's kind of a snake biting its own tail. So when that happens, then you are closing the ring, and then this is gonna be 1, 2, 3, 4, 5 in the ring, with the nitrogens in the one corner. So that's the what is going to be used. So I hope that you miss this possibility. And sometimes you see two reagents like this. Then often cases people miss to answer the right products because I want you to see this thing, how it happens. That's a nucleophile. And then you got two chlorides there. So it really doesn't matter because it's symmetrical. It really doesn't matter which one does it react. First reactions, let's say it happened to the chlorine on the right, then it attacks and kicks it out. So you got amine sitting on the molecule, but now it looks pretty similar to this. You have a nucleophile in one end, leading groups, which is alkyl halide in the other hand. So as soon as these forms, what happens is these kick it out, then you can get the cyclic molecules. Yeah. So this might be a difficult question for you because most time when you see things, most people answer just here. They forget about the possibility of we can actually go further. So that's what I want you to recognize. This was pretty similar to it. You can see that there's an amine here. We got two halide in the molecule. One will happen first. It doesn't matter because symmetrical. One will attack, chlorine will kick out. But you got the nucleophile here, leaving groups there, and they are already very, very close in space. So then it just have to attack again, and then chlorine has been kicked out, then you're going to get the cyclic molecule. So those are something called the intramolecular reactions. So you have to consider this possibility when they're basis. So yeah.
So that NH2 takes out the CO without the other NH.
Give me this proton. Yeah, that just goes out as a proton. It releases HCl.
Which is go out.
Yeah, the solvent just take it out. Solvent acting as a base and just take out the hydrogen. The proton is H plus, can be kicked out the solvent. Even though you can see the proton there, then it must be positively charged. If you see show that, then that's okay. But these are typically neutral, the molecules of neutral forms because of the neutralizing the end anyway. Biochemistry is something that we always ask questions in the test, and then you normally get a lot of questions on these things. So these things are something that you really have to study. Step 2 is pretty simple because it was the inversion of the state in the state center. So that's probably easy to get. E2 is kind of a little bit difficult. That's why we went over one question at the end of the last class, but I guess we're going to do more today. Whenever you're reacting this one with these reagents, then you need to think about biochemistry, which is a anti-coplanar conformation. But anti-coplanar conformation is probably easy for the open chain structures. When it becomes the cyclic molecule like the cyclohexane, then anti-coplanar is an equivalent to trans-diaxial, right? So that's something that I want to remember. The trans-diaxial is the anti-coplanar in cyclohexane. So basically, if you see the halogen there, right, then the hydrogen in the trans relationship in the adjacent partner, that's the one that gets abstracted by the base. But if you see this molecule here, then there's a hydrogen there, but that hydrogen is a cis. So you may think that the base will come this hydrogen here, and then make a double bond, and they could make a more substituted double bond that way. But because of the E to elimination reaction, because anti-coplanar or transaxial conformation, this is actually not produced at all. 0%. It's not even binding. It becomes a 0% main. This one's main. On the other hand, there's a trace hydrogen on this part there, and that's the one pick up the binder base, and the double bonds forms here, and that's the one makes it here. So 100% makes only this one is all because of the anti-coplanar or the transaxial. So this is something that you have to be careful. I'm going to show you multiple examples later, so you're going to keep hearing again. But I just want to explain that why these things are expected. And just trying to show you this anti-coplanar is transaxial. If you remember that, draw the chair conformation of the cyclohexane, right? Then the large substituents in the equatorial is the better, right? In energy terms. But when you do that, the chlorine is actually also on the equatorial positions, and you don't see any of the hydrogen anti to that hydrogen, the chlorine. So no elimination happened to here. In order to eliminate it, you have to flip the chair to less stable conformations, meaning that now these isobutyls are taking axial positions that raise energy, so they don't want to stay in this form. But now you can see that hydrogen is available opposite side of chlorine, and this is an anti-coplanar, or we call trans-diaxial. Now these less energetically stable conformations are ready for the elimination reaction. So that's why the reactions are slow. This is not happening, right? So that's something that you have to understand.